Good afternoon, dear colleagues. Your attention is invited to a report on the topic: Exact and Approximate Solution Problem of Managing the Reserve of Capacity of ARCs, a Communication Network. The work considers the problem of managing the reserve capacity of ARCs, which is relevant in the distribution of flows and design of reliable communication networks with discrete parameters and a constraint on delay time of flows or average load factor of network ARCs. Algorithms for exact and approximate solution of the problem for linear and nonlinear ARCs cost functions are proposed. The experiment results showed sufficient accuracy and speed of the approximate algorithm, which allows us to assert its practical applicability for engineering calculations on networks of large dimensions. The present work is an addition to publications 1 to 3, in which the problem of choosing the capacity of ARCs, PCCA, for communication network from a given set of discrete integer values with constraint on flows delay time was considered. Constraint on the delay time of flows TAV in a network has the following form, where FKL a fixed ARC flow value for KL, E a set of ARCs of a network, WKL a bandwidth capacity of the ARC KL, Tmax the maximum of flows delay time in a network, U sum a total flow in a network, UJ a value of the flow from a node I to a node J, S a set of pairs of indexes corresponding nodes in a network. Delays of flows TKL on ARCs are defined as: when approaching the magnitude of the flow on the ARCs to their carrying capacity, the delay increases and, therefore, network congestion can occur. For the design of data transmission networks, PCCA was studied in detail in 4.5. This problem also arises in transport networks when distributing flows according to the criterion of the minimum cost of the network and a given constraint on the delay time of flows. 6. Problem of managing the reserve of capacity of ARCs, PMRCA, is to parametrically solve a PCCA problem, in which values Tmax with the given sampling step are selected as a variable parameter. As a quantitative measure of reserve capacity, the average load factor of the network ARCs can be taken. Topical issues are the affiliation of PCCA and PMRCA to the class of NP-hard problems and the development of approximate time polynomial algorithms. The article presents algorithms for the exact and approximate solution of the PCCA and the results of their experimental research when parameter Tmax is being changed on a network containing 10 nodes and 30 ARCs, and on a network containing 1,000 nodes and 4,000 ARCs. Problem statement and algorithms for exact and approximate solution. We consider a direct connected network G, N, with a set of nodes N, and a set of ARCs E. In the network for each direct ARC KL, there exists a back ARC LK. An integer flow matrix U is given on the network. Let WKL be a sought for a bandwidth capacity of ARCs of the network in transport blocks. WKL are ascending positive integers, DKL are the ARCs lengths, CKL are discrete values cost of ARCs, such that FKL are fixed total flows in transport blocks, a flowing along the ARCs of the network, where UIJKL is the flow of transport blocks from I to J, which passes along the ARC KL. It is required to find the minimum value of the network cost function, 1. Subject to restrictions, 2. For the parameter of selected values Tmax, that varies within the following limits, 3. Where WKL min equals. To estimate the bandwidth reserve for each solution WKL from Tmax, we will calculate the average load factor of ARCs for the network. 4. Note that the problem 1, 2 can be represented as a knapsack problem with Boolean variables and multi-choice, which is a NP-hard problem 7. Let Cij be a discrete values cost of arcs I with capacity Wij and length di. Tij are delays of flows on arcs. Fi is a flow on the arc I. Suppose that Xij equals 1 if for the arcade I the capacity Wij is selected, and Xij equals 0 otherwise. We are to find minimum function, 5. Subject to restrictions, 6, 7, and 8. Here, the required throughputs Wij correspond to the optimal solution Xij of the problem, 5, 8. For the knapsack problem with multi-choice, 5, 8, there are exact pseudo-polynomial algorithms and fully polynomial time approximation scheme, FPTAS, 8, 9. Despite the existence of exact pseudo-polynomial algorithms, their application for the parametric solution of the PCCA problem is not justified due to the great time complexity of the algorithms. So, for example, the time complexity of the FPTAS algorithm for solving the classical 0 to 1 MCKP problem is. See Work 9. Therefore, in Publication 1, for solving NP-hard problems, 1, 2, and 5, 8, 2 approximate algorithms were proposed on the basis of the approximation of discrete cost functions by linear ones, and on the method of sequential analysis of options, which was first proposed and investigated in Work 10. It was shown that both algorithms at the final stage of work narrow the range of admissible solutions to two values Wij, and with a complete search of the two E-variants, allow obtaining an exact solution. Let us write the abbreviated problem in the form, 9. Subject to restrictions, 10, 11, and 12. Where Cij are discrete values cost of arcs I, Tij are flow delays on arcs I, Fi is arc flow on I. Problem 9, 12 can be transformed into a 0 to 1 knapsack problem, 13. Subject to restrictions, 14, 15. Where problems 9, 12, and 13, 15, are also NP-hard, in general case, there are no exact polynomial algorithms to solve them. 7. In Books 8, 9 one can find a description of 3 exact pseudo-polynomial algorithms for solving problem 13, 15, based on branch and bound methods and dynamic programming using Lagrangian and LP relaxation. C++ program listings for these algorithms, expnap, mincnap, and combo, can be found on DPZanger's web page. These books also provide fully polynomial approximate schemes, FPTAS, for solving the 0 to 1 KP problem. Experimental studies and numerical results. The problem was solved using examples of networks with n equals 10 nodes and E equals 30 arcs, and n equals 1000 nodes and E equals 4000 arcs generated using a pseudo-random number sensor. The lengths of the arcs DKL, in both examples vary from 20 to 50 km, and the flows Uij vary from 1 to 2 transport blocks. The values FKL were obtained distributing all flows along the shortest paths by a 2-criterion lexicographic algorithm. 15. The throughput capacities of the arcs were set by the set 5, 10, 15, 20, with the discrete step 5. The cost values, in conventional value units, of the arcs for the given set of throughput capacities were calculated using the formula. For linear functions, the coefficients and were selected from sets 0, 0, 0, 0, and 5, 10, 15, 20. For nonlinear functions, the values were chosen from the set 0, 0, 0, 0. Value equals 5, and the following. Grow by a random value from the interval 5, 10. The number of values in the sets for WKL K0, K1 was determined depending on the maximum flow along the arc KL, the discrete step of the throughput capacities of the arcs, and the initial value Tmax. If for the current value Tmax it turns out that, then the set is automatically expanded to the value where are rounding signs to a larger integer multiple 5. In Figure 2.3 it is shown the main results of solving the problem for linear cost functions for n equals 10, e equals 30, and n equals 1000, e equals 4000 when the delay constraint is changing from Tmax equals 0.002 to Tmax equals 10.0. Similar results were obtained for nonlinear functions. When solving the problem with an exact algorithm for a network with n equals 10, e equals 30 and linear cost functions, the cost of the network and the average load factor of the arc change, respectively, from 758,165 to 9,815 conventional units, cost reduction from 100 to 98.71%, and from 0.009 to 0.723. If Tmax equals 0.9, the lower bound of the network cost is reached for the linear and nonlinear functions, which cannot be improved by further increasing the value of Tmax, while the exact and approximate discrete solutions coincide, and the average arc load factor being equal to 0.723 is not changed. The most interesting solution options for analysis and decision-making on the choice of the reserve capacity of the arcs are Tmax equals 0.002 and Tmax equals 1.0, in which the cost of the network is significantly reduced, by 98.71%, and the load factor of the arcs increases from 0.009 to 0.723. These variants of solutions for linear functions are shown in Figure 2. When solving the problem using an approximate algorithm for a network with n equals 1000, e equals 4000 and linear cost functions at Tmax equals 7.0, the lower bound of the network cost of 378295008 was reached, which cannot be improved by further increasing the Tmax value. At the same time, the maximum 0.995 average arc load factor is achieved. Variants of solutions for linear functions at Tmax equals 0.002 and Tmax equals 0.04, in which the cost of the network decreases by 308476576, 43.9%, conventional units, and the load factor of arcs increases from 0.389 to 0.912 are shown in Figure 3. Similar results were obtained when solving the problem using an approximate algorithm based on the method of sequential analysis of variance, which is given in 1. However, the time complexity of this algorithm is several orders of magnitude higher, and it took from 5 to 12 seconds on a PC with a clock frequency of 2.66 GHz to calculate each variant of the solution for given values of Tmax. An algorithm based on linear approximation of discrete cost functions coped with such tasks in fractions of a second. Approximate greedy algorithms have a polynomial estimate of the time complexity and do not give large errors with a small scatter of the values of CKL and TKL. In this regard, the work of Cerdiera and Barcia 16 is interesting, in which considered was a formal approach to the problem of representing the exact characteristic the sets of weights TKL for the 0 to 1 knapsack problem, when a set of possible solutions form a matroid. It was shown that in this case, greedy algorithms allow obtaining an exact solution for arbitrary values of CKL, but the conditions on the spread of the weights TKL, which can be verified in polynomial time, are very limited. The conducted experimental studies showed that it is reasonable to apply the exact algorithm of a full enumeration of variants based on the generation of a sequence of binary reflected gray codes 3, when the number of arcs does not exceed 30-35. However, it can be successfully used in various branching schemes, for example, in branch n-bound methods, when part of the variables are fixed and the number of free variables in the branching nodes is small. The approximate polynomial algorithm showed sufficient accuracy and speed, which in most cases allows it to be used for engineering calculations on networks containing more than 1,000 nodes and 4,000 arcs. The PMRCA solution can be useful in solving practical problems of flow distribution and designing reliable communication networks with discrete parameters and a constraint on a delay time of flows or the average load factor of network arcs. See Works 6, 17, and 18. Conclusion. The work formulates the problem of managing the reserve capacity of arcs in a communication network with discrete parameters when the constraint on the delay time of flows is changed. An exact and approximate polynomial algorithm for solving the problem for the cases of a linear and nonlinear arc cost functions is proposed and the results of their experimental research are given. For the exact solution of the problem on the network with the number of arcs no more than 35, the algorithm of full search of options with a limited enumeration of the values of the objective function and constraints founded on the application of binary reflected gray codes. The approximate algorithm is based on the approximation of the discrete cost of arcs by linear functions. The results of the experiment allow us to assert the practical applicability of the approximate algorithm to solving a problem on large networks containing more than 1,000 nodes and 4,000 arcs. The proposed mathematical models of the PMRCA problem, as well as methods and algorithms for their solution, can be used in design and modernization of transport networks and data transmission networks with the technology of virtual containers. Thanks for your attention.